Hello everyone and welcome to another video. So today I'd like to continue our discussion on Fourier analysis by starting down the discussion of one of the most powerful algorithms in modern scientific computing, and that is the discrete Fourier transform. So just to set the stage, remember what we were talking about. So in some of our previous videos, we talked about the Fourier series, right? And in the Fourier series, we introduced the idea of basically being able to take some function, some analytical continuous function f of x, and then try to decompose this into a bunch of other cosine and sine waves, right? So we had these kind of harmonics, right? And we would try to take all those in a continuous fashion and turn them into a representation of this function, which we assumed was periodic on some range and period p, right? That was the idea with the Fourier series, right? And then in our next video, we also discussed the Fourier transform, which was just the concept of taking this period, instead of going from zero to p, and just extending that from minus infinity to positive infinity. So that was the Fourier transform. The reason I'm harping on all of this notation is just to start off this discussion with the fact that the idea with the discrete Fourier transform is a little bit of a poor use of nomenclature, because what we're going to do now in the discrete Fourier transform is we want to think about the situation where, what if we didn't have a continuous function like you see here? Now in this digital age where a lot of data is actually sampled, you might not have this analytical complete function. Instead, what we're going to have is we're going to have samples at discrete times, okay? And the idea now with the discrete Fourier transform is we would like to take this sampling, all of these red dots, and what we are going to try to do is then create a discrete representation of a periodic function. So we're going to basically try to do something similar here, where we are going to try to come up with a discrete version of these basis sinusoids, okay? But we are going to be assuming that these are a repeating periodic discrete sequence with period p. So again, what we're doing here is we are just taking these samples, and again, I want to just highlight a little bit of this notation to make sure we're all on the same page, right? So the original Fourier series, that was dealing with continuous functions with period p, right? Then the Fourier transform was continuous functions, but now going from minus infinity to infinity. So really, what I just described here, maybe it should have been called the discrete Fourier series, because what we're doing here is we are having a discrete function, but it has a period p, just like how the Fourier series had a period p. So again, this is a little bit of an unfortunate name that, personally, I know it caused me a little bit of confusion when I started thinking about these and started investigating these, but we're just going to go with the nomenclature. So when we hear discrete Fourier transform, we have a discrete function with period p, okay? So this is still going to be a periodic repeating sequence that we are generating using these base sinusoids. So that's the game plan. So again, that's the introduction. Tell you what, why don't we go ahead, and before we actually dive further into this, I want to take a little bit of a sidestep into what appears to be a slightly abstract mathematical concept. Okay, so before we jump into this, the little detour I want to take is to discuss this idea of roots of unity. And this is actually a really simple discussion to start off with. In fact, anyone, I've got two young girls, and I can probably ask them this question, and they can probably answer it. I asked them, what is 1 raised to the power of 2? What's 1 squared? Well, it's just 1, right? What's 1 cubed? It's just 1. What's 1 to the root 2? Or sorry, to the 1/2, right? This is just root 2. 1 to the root 2. That's just 1. 1 raised to the third, 1, right? I think everyone gets the pattern right now, right? You can basically raise 1, or unity, to any stinking power you want. It can be fractions, it can be whatever. You still get 1, right? So this is almost like the dumbest line of math I think you're going to see me write up ever, right? It's just 1 equals 1, and you can raise it to a whole bunch of powers, right? Now, where this gets interesting is, what about, if you remember our discussion on complex numbers, right? We had a separate dedicated video on complex numbers. We could think about a number in a real imaginary plane, right? In a complex plane. And in this case, where is this thing, if I have a point here in the real complex plane, right? I can write this as a magnitude and an angle, right? Or e to the theta I, right? So if I want to use the kind of Euler formulation of a complex number, right? I can visualize this point as, again, it's just a unit vector with length 1 with an angle rotated theta, right? Okay, so now in this question, where is the number 1? Well, the number 1 is right here, right? So this is 1, or 1 plus 0i, right? It's just 1, right? It's right here. And I think everyone will agree that this vector here in the complex plane, it's just at angle of 0, or it's also at an angle of 2 pi, right? Or it's an angle of 4 pi or 6 pi, or any multiple of 2 pi will also get you to this number 1, right? So does everyone agree that e to the 2 pi I is 1, right? That's one full wrapping of, gets you back to 1. So again, this is not anything fancy, but let's combine this with the fact that we just said, hey, I can take this number 1, or unity, raise it to any power, and you still get 1. So that's all I'm going to write here, right? 1 to any power. Let's call this power k over n, right? So you get this expression. And let me just remember, powers, right? I can move this k over n in by just multiplying these two together, right? So I get this expression. This is what's sometimes referred to as the nth root of unity, okay? Because again, as k goes from, 1, 2, 3, whatever, and same thing with n goes 1, 2, 3, whatever, this stays 1, right? Now, if you have the special case of k is equal to 1, so again, all you're going to do is just consider this to be a single 1, right? You end up with this expression, right? This is sometimes what's referred to as the primitive nth root of unity, okay? Because it's the first one, or you can keep adding k of 2, 3, 4, 5, 6, and you'll still get different wrappings of this expression, right? So again, this is referred to as, again, as the primitive nth root of unity. And again, I just want to bring this up now because stick this in the back of your mind. We're going to revisit this and leverage this later. This notation is going to be a lot more convenient. So again, all we're going to really do is just define this here as the primitive nth root of unity, right? And then these are the nth roots of unity where k is 1, 2, 3, 4, 5, etc., etc. And again, now you can kind of see where the notation or this name came from, right? We've got 1, and it's not the square root, it's not the cube root, it's just the nth root of unity. And again, unity, instead of 1, we're just going to use e to the 2 pi I as a fancy way to write 1. So again, keep that in mind. We're going to use that more. All right, so now let's go ahead and spend a couple of minutes deriving the actual discrete Fourier transform, or DFT. I think a lot of texts or references, if you look up what the DFT is, they'll spit it out. They'll say, here's the DFT, here's how you compute it. But I don't see a lot of references actually deriving it from first principles. So I want to spend some time doing that right now. So if all you care about is just the end result, feel free to skip ahead. The timestamp is in the description of this video if you want to just jump ahead. But if you're interested, let's get into that right now. So the idea, right, with the discrete Fourier transform is, again, remember, we have some continuous function or underlying process which might generate this f of t signal. And again, this is a analytical continuous function, right, if you want to think about it in that respect. So right now, what you could do, right, is sure, you could go ahead, pick some period p, and compute the Fourier series, right? We talked about how to do that. Or if you don't want to pick some small period and you want to get the entire thing from minus infinity to infinity, you do the Fourier transform, right? But what we're going to actually be interested in doing is saying, what happens if I go ahead and sample this function at certain times and the only information I have are the sample values? So in other words, what I'm going to do is, let's start here at x equals 0, right? So there's no loss of generality there. You could always shift the signal or the axes to start here. But let's say our first data point is right here, okay? And we are going to go ahead and let's call this is going to now be, let's call it f0, right? Because it's the function value at k equals 0, or if we want to be explicit about this, we're saying f0, it's the function evaluated at 0. And I'm going to write it like this, 0 times delta x. Okay? Because what I'm going to end up doing with this delta x is I want to be able to say, all right, I've got one sample here. Let's go ahead and grab another sample here. This is now f1, right? And the idea with f1 is that it is spaced a distance delta x away. Okay, so again, to be explicit, f1 is nothing more than the function, but it's sampled at 1 times delta x, right? And you can keep going on, et cetera, et cetera. So I'm going to go ahead and draw this. So let's keep sampling this, and let's get like 6 samples. Okay? So here's another delta x. So here would be f2. All right, so here we have our 6 samples. So again, in this case, I'm going to choose n, which is the number of samples that we're going to take, as equal to 6. So here's the picture that goes along with it. Here's the definition of all of these signals, so you see, or these samples. So you see, it's really nothing more than 6 numbers. So really, let's call this like a sequence. Maybe let's call this some sequence of samples. Let's call it fn, right? So n goes from 0, 1, way, all up to, capital N minus 1, which in our case is 6 minus 1 or 5, right? So this means you have 6 samples total that goes from the index of 0 to n minus 1, right? So again, all this set it's just these numbers, right? It's just f0, f1, f2, f3, f4, and f5. Right? It's just a list of numbers. And in fact, I like to think of these, you're going to see later that this is helpful to think of these as just like a big vector of f0, f1, f2, f3, f4, and f5. So again, I'm just writing this out explicitly just so we can see the dimensions, right? So this sequence of samples, it's just a vector of 6 numbers or n values, right? That's all you have. So the idea with a discrete Fourier transform, right, is you don't have the underlying blue curve. All you have are those orange dots, right? You have a vector of 6 numbers, and we want to see if this can be used to kind of extract frequency information or frequency content of the underlying signal, right? That's the idea, okay? So now, what's interesting, and this is the part where, again, we talked about this earlier, that this misuse of the word, I guess, transform versus just normal discrete Fourier series, right? This one, what I'm getting at here is what we are now going to do is we are going to assume now that this orange sequence of dots repeats with a period you can kind of see here. The only small caveat here is that, okay, let me draw one more sequence of this repeating system here, right? So again, we don't know about the blue curve. Instead, we just have this repeating sequence of dots, right? So again, the next dot is going to be, I'm going to try to match it. It's going to be, right? This F0 is just going to repeat, right? And then we're going to assume that F1 repeats, so it's over, I don't know. I'm trying to make these accurate, like this, right? And then F2 is up higher, right? And again, all of these have a distance delta x, right? Okay, and again, give me a second to kind of repeat this picture. All right, so I finished drawing another sequence of the repeat, followed by a third iteration of the repeating periodic signal or sequence. The thing that I wanted to point out, a couple of things here, is, again, notice here that there were n equals 6 samples, right? And one common mistake I see people make is that they assume that the period of this sequence here is this, right? Because that seems logical, right? But notice there's one extra frame here before the sequence starts repeating again, right? Because this one, right, which matches with F0 is a repeat of F0, it takes 1 delta t to get there, or 1 delta x. So there's an extra frame here, delta x. Right? So really the period is like this, right? So the period of this sequence looks like this, which if you look at this long enough, right, this period, it's just nothing more than n times delta x. So just don't be off by 1, right? Make sure it's n times delta x. I've seen some people put n minus 1, but it's actually n, right? So again, here is your first iteration of the periodic sequence, right, in orange, followed by, again, your second iteration here in purple, and again, we got to make sure we're taking into account that extra delta x, right? So this here is your second iteration or repeat of the periodic sequence. And then the last one, just for giggles, is over here, and again, we're going to add on our extra delta x before it repeats again. So again, here you have your third periodic repeat of the sequence. right? So again, this is what I just wanted to show and talk about, and you can clearly see here that what we're doing right now is we're kind of come up with an approximation of this repeating periodic sequence with period p. So again, this you might want to consider this in your mind as a discrete Fourier series, right? Because it is not a discrete Fourier transform. We're not getting it from minus infinity to infinity. We still have this periodicity of period p. All right. Okay. So that's great. Now that we understand that, let's go ahead and erase these second and third ones and just focus on this one sequence of data that we've got. Okay. All right, so we're back. I've erased all these other repeats. We've just left the first set of actual data and samples that we have. So again, we're going to take into account this last delta x, right? And we see now that we have this period. Let me extend these lines a little bit further down. We're going to use them in just a second, right? So this sampled sequence has a period of number of samples times the spacing in the samples delta x, right? Okay, so that's the period. Now, again, what's the whole idea with this whole Fourier series discussion, right? The idea is we're going to try to decompose this sample, or you can think about it like the blue function underneath the samples if you want, right? If you want to think back in the continuous time, what we were doing with the continuous Fourier series is we said, all right, we're going to assume you've got this blue function underneath, then we're going to try to fit or build up the complicated blue function with a series of lower frequency sine waves, right? So the lowest frequency sine wave or cosine wave that you're going to try to fit in this period, I think everyone would agree that what you would do is fit one cycle in this period, right? So in other words, what you're going to try to do is I'm going to try to sketch this as best as I can. You're going to make something like this, right? Okay, this is like the slowest frequency sine wave, right? So it completes one cycle in one period, right? So I just wrote that here that says, right, the idea is we're going to start off with the lowest frequency sine wave of this period. It's got one cycle over this period p, right? So we can just write that down. The ordinary frequency, it's just one cycle per p seconds. Again, we're going to assume that x, usually the independent variable x is time. So you can think about this as seconds, whatever. So you basically get, okay, one cycle over the period of p is n times delta x, right? So again, this is your ordinary frequency in units of hertz, right? Because this is how many cycles per period are you completing, right? So this is your ordinary frequency. Let's call it c or something like that. This is going to be the lowest frequency sine wave. Well, technically the second lowest frequency, but you're going to see that in a second, right? Okay, so this is your ordinary frequency. We can easily convert that to angular frequency, right? It's just angular frequency is 2 pi times your ordinary frequency. So this is the angular frequency of this cosine wave here that we're going to try to fit. Okay, and again, I'm playing a little bit fast and loose because, again, if you watched our previous videos, you know that it's actually a complex sinusoid, right? There's a cosine plus I sine component. Let's just look at the real part just to make the discussion a little bit easier, right? So let's call this thing here, I'm going to call this, this is like the real part of, let's call this function sk, okay, of x. Okay, so that's this right here. And again, all we're saying is that that green function, it's just a cosine wave with this angular frequency, right? Now, the thing is, this is for when k is equal to 1. Okay, so this is the k equals 1 case, right? It's the really, really slow frequency, right? But what we're going to also do, right, the whole idea of Fourier series is you could potentially fit with another frequency, another cosine wave, which is periodic on this period p, but has a higher frequency, right? So the next one, instead of completing one oscillation per time step, right, you are going to try to complete 2. So again, oh boy, I'm gonna probably butcher this drawing, but okay. So here's the k equals 2 case, right? So to capture that, I can just describe that here. Right? I'll just put in an integer k here. So now k is going to run from 0, 1, all the way up to n minus 1, right? So what we're basically describing, this function sk, it's these fundamental harmonic frequencies, right, that we are using to build up a basis of this Fourier series, right? So these are like the basis functions, if you want to think about them that way, right? And again, I'm just displaying the real part here and drawing the real part. We'll get into the full bit in just a second, but I want to make sure we're all okay on this. Okay, so the last bit that I want to get into is, remember we discussed that that this k equals 1, I called it the lowest frequency sine wave, but really it's actually the second lowest, right? Because the lowest is actually when k is equal to 0, right? When k equals 0, you basically just have a flat constant, right? So actually, the k equals 0 base sinusoid, right? It's just a flat constant, right? And we saw that in our earlier discussion. You might need this DC gain of 1 or of unity function to go into your system, right? Okay, so yeah, I think that's pretty good. So tell you what, now that we have a rough idea, right? Again, the idea is pretty simple, right? All we're going to try to do is build up the periodic function using these base sinusoids, right? Same thing that we did with Fourier series, okay? Now, remember in our discussion with the alternate forms of the Fourier series, right? We showed that, okay, the actual full equivalent complex sinusoid, right? We can use Euler's form to basically write the exact same thing, right? So this is what it looks like, right? So you got e to the I, and then same idea with the angular frequency shows up here, and yeah, that's pretty much it, right? This is the same thing. Now, again, remember, what's really interesting is note here that I can pull out this kx and then delta x, right? So kx in the numerator, delta x in the denominator of this exponent, pull it out so I can rewrite this line to look like this, right? If you remember that the whole discussion on the primitive nth root of unity, that's what this is right here, right? So you can almost think of this primitive nth root of unity as almost defining like the lowest sort of base frequency that we saw over here. So all we're doing is we can rewrite this as this, right? I can use now this primitive nth root of unity expression here to get this describing function. So this is the actual basis function that we're going to be using for the discussion, right? So what's interesting about this is, again, in the interest of complete full disclosure, right, you write this thing out using Euler's formula, right? And here it is. Here's the cosine part, exactly like we were just looking at, right? That is the same as this, right? These two things are the same, right? But then we got to remember that there's the plus I sine of the same thing, same angular frequency, so to speak, as well, right? So this is really the basis functions that we're using. What we're plotting over here is, again, it's just the real component because I don't want to have to draw the I sine part as well, but you get the idea, right? It's just sinusoids of increasing harmonic frequencies that we're going to use to build up the function, right? That's all we're talking about, okay? So here, let's use this notation, s sub k of x, right? Because again, this is a function in x, right? And as k increases from 0, 1, 2, all the way to n minus 1, you just get higher and higher frequencies of these sinusoids, right? Okay, so this is the continuous function. Now, remember, we're talking about the discrete Fourier transform, right? So all we're going to do now is I am going to now sample these sinusoids at the exact same point. So, do I have a picture for this? Yeah, let me use another color. I'll use red, okay? So all we're going to do here is at these same times, I just want to sample this k equals 0 sinusoid. I'm going to sample it at the same times that I'm doing my other function, right? The original function, right? So I'm going to generate these red dots. That's it, right? Same thing for the k equals 1. I need this dot, and then I guess, let's see if I can draw this so it looks reasonable. I'm going to have to line myself up. Okay, so we've got all the little red dots. The way we're going to get these red dots, get their actual numeric values, right, it's really simple. All we're going to do is we've got the equation of the green line, right? All these different green lines for all the different k's. We just have to go ahead and evaluate this at these k locations, so we're going to start here at 0 delta x, 1 delta x, 2 delta x, etc., right? So we're just going to evaluate it at these very specific x locations, right? So all you do is, like I said, plug this in for x equals, let's start with this first sample. So let's get this dot right here, this one specific red dot. That's just the basis function for k equals 0 at 0 times delta x, right? So it just turns into this, right? It's just take this expression right here. I think it's easiest to work with this expression that uses the primitive nth root of unity, right? And just plug in k equals 0, x is equal to 0 times delta x, right? So you end up with this. I'm going to leave it with the k here for now, just so you can see what the pattern looks like, okay? So this is this very first red dot here. Let's get the second red dot. So now I'm going to leave k equals 0. I'm going to move to the second sample, right? So now I'm going to use 1 delta x. So all you got to do, it's really easy. In fact, let me use a different color so we can see what changes. It's just this 0 here turns into a 1, right? So now, oh, sorry, I'm looking at sample 1, right? So now this turns into a 1, right? And again, you just end up with a 1 here, right? So that gets us this second sample, right? Etc., etc., etc. I think everyone sees the pattern, right? Now, let's also now have a look at this one. So this next sample, this next complete basis function is now a different k. So now k becomes 1, right? So all that changes here is this k changes, and the whole idea, everything else stays the same, right? So in general, right, you can generalize this. You can describe every single one of these red dots with this sequence description, right? All we're doing here is that to get the nth sample, so again, n is going to run from 0 starts here, n equals 1, 2, 3, all the way to n minus 1, right? And this index k goes from k equals 0, 1, 2, all the way down to, probably should have written this down, right? It goes all the way to k equals n minus 1, right? And at that point, you've got some, I'm probably butchering this. This might not be accurate, right? In fact, this probably should have started up here, right? But you've got some high frequency sine wave that, again, we are just going to sample at these locations, right? That's all we're doing, right? So again, maybe we should write a little bit of some dots just to make everything the same, right? So this is dot, right? You can have all of these different basis functions that we're sampling, and here is going to describe the sequence, right? And what's fascinating about this is, again, it all comes down to this primitive nth root of unity just raised to some power of just n times k, right? So this sequence, what this looks like, it's just a series of n numbers, right? So this sequence right here, again, you can just plug in k equals 0. This sequence here describes these, in this case, 6 red dots here. K equals 1 describes these 6 dots here. K equals 2 describes these 6 dots, etc., all the way down to k equals n minus 1. This sequence will then give you these red dots, right? So again, this is really fascinating. All this is it's just the sampled version of the basis sinusoids described as a sequence, right? So this is fascinating. Again, here's the expression for it. Let's write it using the definition of the primitive nth root of unity, right? You just get this. So here is the takeaway equation that let's just use this. Let's keep this thing in mind, that this blue thing is what we end up with. This is what's generating all of the samples, right? And this is where this gets really interesting. Okay, so let me clear a little bit of space. Let me get rid of this. Well, yeah, I tell you what. Let's do this. You will see the picture. Okay. So what we're going to do now is let's go ahead and draw the real imaginary axis, the complex plane. Let's put a unit circle on this. Okay. And now, what's interesting about this is, remember our primitive nth root of unity, right? If you think about this long enough, this is basically breaking up this unit circle here, 2 pi, into n chunks, right? So in our case of 6 samples, what we've got here is that there are now 6 locations on this circle that are equally spaced apart. I think it's something like this-ish. Right? Okay? And now what we can do is let's use our expression here to evaluate where these sample points fall for a given location. So in fact, let's go ahead and start. Let's do this. Let's start here. Let me again use a different color over here. Let's get ourselves S0 of n, right? And again, what this should be is there should be 6 numbers in here, right? So there's a 5, 1, 2, 3, 4, 5. Okay, well, something like that. There's 6 numbers here. There's a number here, 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 right? So again, all you got to do is evaluate this. So S0 sub n, it's just going to be e to the 2 pi n times 0 over, in our case, 6, right, times I, right? You look at this. Okay, let's start with n equals 0, right? Where does that end up? This is actually I'm going to grab a... let's grab one of these, okay? This is right here, right? Okay, so that's the first sample right here. It's this, and in fact, I think this just comes out to basically be like 1, right? Okay, then let's go get n equals 2, right? So again, if you put in n equals 2 here, you see this also just comes out to basically this whole exponent is 0. So again, you end up in this same location, right? So this same location, in fact, this is the same for all of these, right? For any n, you get this, right? So here, this is going to be for all these cases of, this is going to be your 0 sample, your 1, 2, 3, 4, in our case, goes up to the 5th sample, ends up here, okay? Oh, sorry, my notation is not the greatest. I'm trying to say that these are the which sample numbers. Maybe let me not use this set notation, right? Because really, the values here are 1, 1, 1, 1, which agree with what we talked about here, right? It's just 1, 1, 1, 1, 1, 1, right? Okay? Now, let's go ahead and change this. Let's get the the S1 sequence. Right, so again, let me erase these just so we start from scratch. Okay, so all I got to do now is k is 1 now. Okay, so now you look at this, and I should maybe make sure we change everything everywhere. Okay, so again, let's get the n0, this number right here. Okay, so again, you put n equals 0 here, this just becomes 1. So again, we're sitting right here. Okay, but now when n equals 2, if you look at this, all you're doing is you're moving around that circle by 1/6 away around the circle. In other words, for the next case of my n equals 1, the 0th sample is right here, but the 1 sample is up here, right? That's what goes in here, and I don't want to actually compute out the number. I'm just going to say blah, 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 right? It's whatever this evaluates to. It's e to the, well, I mean, it's really easy here. It's e to the 2 pi something, 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 right? Okay. Yep. Right. Okay. And now you go n equals 2 now, right? Let's get this entry, right? And again, you see that just means n equals 2 here, right? So again, you just move yourself a little ways around. So now here's a 2 sample, and again, you see the 3rd sample and the 4th, the number index 4 and index 5, which is really your 5th or 6th and last sample, goes like this, right? So you just move your way around here, right? Now, again, let's go one more just so we see the pattern and see what's interesting about this. Let's go ahead and get the S2, right? So now we're looking at this one, right? This sinusoid, which actually seems to go around this unit circle faster. It makes 2 revolutions in 1 period, right? So again, let's go ahead, let's reset the picture. All right, okay, reset, let's reset everything, okay? Okay, so we're getting the S2, delete all this stuff, right? Okay, so now k is equal to 2, right? Okay, so now, again, the S, or when n equals 0, the 0th, or the first entry in this set here, again, this just comes out to 1. So again, you're still starting here. So here's 0, right? Okay, but now, when n equals 2, you actually jump by 2 sequences, right? By 2 1/6 sections. So instead, you go bam, bam. So here's the 1, the n equals 1 case, right? And then same thing, you go bam, bam. Here's the n equals 2 case, and then bam, bam. You're back here. So the 3 case is actually here, and then bam, bam. This is 4, and then bam, bam, 5, right? So interestingly, the S2 case, it has you can think of it about having some repeats, right? And again, let's tell you what, in the interest of completeness, let's just go through a few more of these. You'll see some interesting patterns, okay? So let's keep going. Let's go reset one more time, okay? So take this guy off. Let's go ahead and get this all reset, okay? Let's look for the S3, okay? S3, S3. So again, the only thing that changes here is this goes to 3, okay? So now you see by every n iteration, you jump 3 spaces. So here's 0, all right? Now 3 spaces is 1, 2, 3. So actually you're over here. So here's 1, and then 1, 2, 3. Here's the second, or sorry, the 1, no, sorry, this is the 2. Index 2, right? 3, 4, 5, right? So in this case, the S3, it just hops between these two, right? Okay, and now let's go ahead and do S4. I think at this point, everyone's getting the pattern. This is hopefully pretty simple now at this point. S4, K goes to 4, right? And now you see that we're actually jumping by quite a bit now each time, but the pattern is interesting. Okay, so again, you start here with the 0th, right? Now we're with n equals 1, you go 1, 2, 3, 4. So here we are. This is actually the 1. And then 1, 2, 3, 4. Here's 2. 1, 2, 3, 4. Here's 3. 1, 2, 3, 4. Here is 4. And then 1, 2, 3, 4. This is number 5. So again, you see a little bit of symmetry. We saw this pattern earlier, right? And this is going to come back, okay, for us. And then finally, the last one in our case is the S5 sequence, right? Where now we're jumping by 5 every iteration, right? So let's go back, reset everything. 0 starts here. So 1, 2, 3, 4, 5. So here is 1. And then 1, 2, 3, 4, 5. So here's actually 2. 1, 2, 3, 4, 5. Here is number 3. 1, 2, 3, 4, 5. Here's 4. And then 1, 2, 3, 4, 5. Here's sample number 5. So interesting, right? So now it's almost like this idea of negative frequency where it's going the opposite direction. So again, this is all going to come back to us. I just want to make sure we have a good, clean picture. We're seeing all we're doing here with this jumping around this complex circle, right, is generating samples, right, of these basis functions for k equals 0 all the way up to k equals n minus 1, right? So that's all we're doing here, right? Okay, so at the end of the day, what we end up with is we end up with this sequence, right? We have a way now to describe a sequence of samples. Each one of these corresponds to one of these basis functions, okay? All right, so now we can take the next step. Okay, so now we're within striking distance of getting to the final form of the discrete Fourier transform. So let's step back again and recall when we were talking about the derivation of the coefficients for the continuous Fourier series, right? We saw that the way you obtain those coefficients, right, was by taking an inner product of the function with all of the base sinusoids, right? So in other words, it's taking the inner product of this blue line, the blue continuous line, with this green continuous line. That gives you one set of coefficients. Then you do the same thing. You can take the inner product of the blue line with this green continuous line. That got you another set of coefficients, et cetera, et cetera, et cetera. And you kept doing that for all of the different basis functions that you wanted, right? And again, remember that in the continuous sense, right, the inner product with two functions, that involved the integral, right? But now in the discrete sense, it's actually even a little bit easier. We're going to do the same thing, except we're going to use these discrete samples. So we are going to now take an inner product of the function, of the discrete function, aka these orange dots, right? Take that inner product with an inner product with this basis function, its discrete version, aka this set of red dots, right? That's going to get me a set of coefficients. Then I'll do the same thing. I'll take the inner product of the discrete function, again, orange dots, with the next set of red dots. So all we're doing is inner product orange dots with this set of red dots. That gets us a number. Take inner product of orange dots with these set of red dots. Gets you another number. Inner product of these orange dots with the third set of red dots. That gets you another number, etc., right? So that's all we're doing here, right? This number that we're getting is nothing more than the sample of red dots. So again, all you can think about this term right here, this is just the sequence. This is the red dots that we have, or no, sorry, excuse me, this is the orange dots. I got too excited. These are the orange dots, right? F is the actual sample values, right? So these are the actual samples of your signal, or the data that you're trying to perform a discrete Fourier transform on. You take that inner product with each one of those red dots, right? Which again, we saw was just nothing more than going around the unit circle a bunch of times and jumping appropriately by this, this primitive nth root of unity amount, right? Okay, so again, orange dots, we talked about this sequence earlier. I like to think of it as just a vector of numbers, right? It's literally the first sample, second sample, stacked all the way up to the last sample here, right? So it's just a vector. This thing right here, the first thing in the inner product, is just a vector. And same thing, these red dots, just stack them all up. They're just a whole bunch of numbers, right? And again, we saw the way to compute this was just using, again, your primitive nth root of unity, and then it's raised to an appropriate power, right? This is exactly what we just talked about, okay? So let's talk about this. How do you take the inner product of a vector? Keep in mind, though, this is complex, right? So we're talking about a complex inner product. So all you're going to do is multiply this element with this element's complex conjugate, right? Then add it to this plus this complex conjugate, yada, 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 right? It's this sum, right? It's just the sum of the nth element with the nth element of the kth set of dots, right? So again, I like to think about this. Just hold k fixed to start with. Just assume k is 0 and just run this out. This will get you one number, right? So again, keep in mind this is complex, right? This sk. We said that these red dots, you can also write it like this, right? It's just using the primitive nth root. This is what we were just plotting in the previous board. Let's substitute the definition, right? Remember, this primitive nth root of unity showed up so much. I think we better just write it down here so we can have easy reference to it. So I'm just going to substitute that in here, right? So again, this is now e to the some angle I, right? So again, if we want to quickly sketch this, right? This is just some angle, right? That's what this term is describing. So it's complex conjugate, it's just the other direction, right? You just flip it over the real axis, right? So in other words, you can just stick a minus sign here, right? So the complex conjugate of this, it's just put a minus sign here, right? Same thing, okay? And now, again, use your definition of primitive nth root of unity, and we can write it like this, right? And here it is. This is it. This is where we're going for. This here is the discrete Fourier transform, okay? What this is allowing us to do, right, is that you plug in your sequence of data f, right? You have these n data points. You run it through this. I mean, it's a relatively simple equation, right? And this is going to spit out another sequence of numbers, right? But this is going to be a complex number which is going to encode, just like we saw with those Fourier coefficients. This is effectively the Fourier coefficients, right? So this is encoding frequency, phase, there's a lot of information in this, right? Okay, so this right here, again, I think we better just go ahead and write this down. This is the discrete Fourier transform, the DFT. This is how you do it. This is what the operation does, right? Okay, and similarly, you can go backwards. You can do the inverse discrete Fourier transform. That's what this here is, right? So this is the inverse discrete Fourier transform, right? So here you give it the complex numbers which have the frequency content information, and you can use this and go back to the kind of spatial or time domain, wherever you want to think about it, right? And recover the original signal, right? So a couple of things to note here. Look at this inverse discrete Fourier transform. Notice there's a normalizing factor of 1 over n. We're going to see in just a second here that the size of these imaginary numbers can grow just by taking more samples. So this is going to go ahead and normalize that out so that it's that we maintain that this regularization. And then also notice that the in the discrete Fourier transform in the sort of the forward direction, you got a minus sign here. And then in the inverse, you've got the opposite. You got a plus sign here. Sometimes, depending on what text you read, you may see these flipped as this being positive and this being negative. But again, as long as they're consistent, and meaning AKA opposite, it should be fine, right? You should be consistent. So again, the picture that goes along with this is this, right? So these are your sample data in real space, so to speak, or these are all real numbers you can think of, right? This is what's coming off of your microphone or your pressure sensor or whatever you want. This is your data, right? What you can then do is you can use the discrete Fourier transform, aka this procedure, and transform this n elements into another vector of n elements. And this is encoding in all of that frequency content, just like we saw in the continuous Fourier series and Fourier transform, right? Now, you can also go backwards, where if you have this information of frequency content, you can go backwards using the inverse discrete Fourier transform to recover this data, right? So that's it. Again, if you've tuned out for the last half hour, just pay attention to the blue box and the red box. This is the discrete Fourier transform pair, and this is what you're looking for, right? This is what we're going to be using. This shows up all the time. And now what I think we should do is let's look at an example of this. All right, so I moved our definition of the DFT as well as the primitive nth root of unity over here. And now let's look at an example, okay? So what I'd like to do is I'd like to consider this function f, right? It looks like this. It's pretty darn simple. It's just a few cosine waves stuck together. Notice here that this thing is made up of 3 components. So the first component is it's got a constant offset of 5. The second component here, it's a 1 hertz signal shifted by 90 degrees, and it has an amplitude of 2. And then the third component here, it's a 2 hertz signal with amplitude of 3. Okay, so here's a picture. I'll just flash a screenshot of what this function looks like by itself, right? It's not too bad, right? It's just some kind of interesting behavior. Now, what we want to do is we are going to say we don't have access to this actual function. Instead, what we've got is we've got a bunch of samples of that function. So let's choose a sampling rate which is at least above the Nyquist frequency, right? So it's got to be at least 2 times faster than the fastest signal. So in this case, it's 2 hertz. So we need at least 4 hertz. Let's just go a little bit higher just for giggles. Let's go to 5 hertz. Let's sample at 5 hertz, which means we have a delta x of 1/5, right? Okay, and now we can also now pick how many samples are we going to collect. Let's collect 6 samples here, okay? So now that we know how many samples we're collecting, we can actually compute right off the bat the primitive nth root of unity, right? So it's just plug in n equals 6, and yeah, you end up with this, right? It's just a complex number again, right? And we saw that what that represents is basically how much of this unit circle are we going to be, what kind of resolution are we chunking that up into, right? Okay, so we got that. Now, all we can do is we can go ahead and sample the continuous function every 1/5 of a second, right? And we're going to obtain some samples. So again, I'll show you a screenshot of, I did this in Mathematica. This is what it looks like, right? You've got all these red dots, right? I apologize. I switched the coloring. I guess these should have been orange dots in order to go with our previous convention, but that's okay. All we care about is we sampled that function. We got a bunch of numbers out of it, right? That's the only information we have about the function or the signal, right? So these are the numbers. Here's the approximate numerical value. So this is all that gets dropped into your lap, right? You have this sample of the function. So you got these, we got these 6 numbers: 8, 4.5, 7.1, 4.8, 0.7, and 8. It's not a lot of information, and now we're going to ask ourselves, are we going to be able to extract any information out of this using the discrete Fourier transform, okay? So let's go ahead and do that. Let's compute the DFT, okay? So we're just going to compute it using this equation over here that we just derived. So let's start with k equals 0. All right, let's just start with the first case and we'll see what happens. So I'm going to use blue indices to denote the k values because I think this is going to show some interesting behavior that I want people to kind of, let's all pay attention to this now so we can bring this up a little bit later, okay? So k equals 0, let's compute f0, or f hat 0, right? Okay, so to do that, you just kind of plug it in. It's just that summation, but now k is equal to 0, okay? So again, you can write this sum out as 6 individual terms. It just looks like this, right? Okay? So again, this is all 0, 0, 0. So actually, all you got to do, if you notice, all of these are basically 1s. These omega n to the 0th powers, these are all 1s. So really, you just need to plug in this f0 number is 8, right? f1 is 4.5. f2 is 7.1. f3 is 4.8. You get the picture, right? So you plug all this in, you do all this math, you end up with just a number, right? And in fact, you end up with just a real number because all these imaginary things are 0, and I think you end up with 33-ish. Okay, so f hat 0 is 33, and again, I'm going to start building up f hat as a big vector. Okay, so we just got the k equals 0 term. So now let's change this to k equals 1, and this is where this gets interesting. The equation does not change by very much at all. All we got to do is take all of these zeros everywhere in blue and replace them with 1s in blue, right? That's the only thing that changes. Okay, so for the case of k equals 1, it's just 1, 1, 1, 1, 1, 1, 1, 1. Right? That's literally it. That's the only difference. Okay? So again, you plug in all these numbers, and now you see that this primitive nth root of unity comes into play because some of these terms, this is still going to be a 1 here. In fact, this is always going to be a 1. Keep that in mind. We're going to see that later. But all these other terms are non-zero, right? So this imaginary bit is going to come in here. So f1 is actually most likely going to end up being imaginary. So f1 hat, okay, I think this comes out to 5.6-ish minus 2.5i, something like that. Okay? Okay? Great. Now let's do it again. All I got to do is, again, change these blue 1s to 2s, right? So hopefully by this point, some stuff is going in your head and you're saying, wait a second, there might be a more interesting way to do this. And in fact, yeah, we're going to look at that in just a second, right? But first, let's just be complete and just, that's all that changes, right? Oops, sorry, there should have been a 2 right here, but I guess this 2 doesn't matter because they're still multiplied by this 0. Again, this term turns into a 1. This is always a 1, right? Okay, so again, you crunch all these numbers and you end up with the 2 case. This is a 2.6-ish plus 8.6i. Okay? All right, and then let's just keep going for completeness. Change all of these 2s now to 3s. 3, 3, 3, 3, 3, 3, 3. So you're seeing the only thing that's changing is basically the powers of this primitive nth root of unity, right? Okay, so now 3 here, this comes out to negative 1.5. Okay, and then let's go ahead and change all of these to 4s. Oops, this should be a 4 also. So okay, there's 4, 4, 4, 4, 4, 4, 4, 4. Okay, so again, let's be complete, just so we're not skipping any steps. Sometimes I hate it when people just like wave their hands and skip steps, right? But we're going to be a little bit clean. Okay, so again, you plug in all the numbers and we end up with, this is interesting, you actually end up with 2.6 minus 8.6i, which if you notice, I'm just going to draw your attention to the fact that this one mirrors this one. They're complex conjugates. So basically, these two numbers have the same magnitude, but just different phase angles associated with them. Okay, fine. And then lastly, let's do k equals 5. Okay, so again, all of these 4s just need to change to a blue 5s, right? And then we're done, right? So this is 5, 5, 5, 5, 5, 5, 5. Okay, and then you come up with this as being 5.6 plus 2.5i. And again, let me draw your attention to the fact that this one mirrors this one from a complex conjugate perspective. So again, what's interesting is you're starting to see some symmetry fall about the middle, right? So the middle, like this chunk is mirrored by this chunk, and that's going to have some ramifications down the road. I just want to draw your attention to it right here. Okie dokie. So that's all you got to do, right? So you're just turning the crank with this equation a couple of times to get these numbers, right? So in fact, turning the crank sounds boring by hand. I think it's useful to do it once or twice by hand just to get some insight and to see this structure that goes along with the calculation. But in reality, let's go over to a computer tool and let's just take a quick look at how we might code something like this up. All right, so here we are in Mathematica. I think I've already defined all these samples here. Yep, here they are. In fact, well, let me make these numbers so we can see. Yep, here are the 6 numbers, right? These are my sampled version of the signal. Here's, you know, the 8, the 4.5, 7.1, et cetera, right? So now all we're going to have to do is just run it through our equation. So I'm just going to go ahead and do this now, right? So going from k equals 0 to basically n minus 1, right? So the kth f hat entry, it's just I got to sum up all of the normal standard entries and multiplied by the appropriate power of the primitive nth root of unity, right? That's all we're going to do. And again, the only thing to maybe note here is Mathematica is a one-based indexing system. So I have to be a little bit careful that this here, when k equals 0, I'm actually trying to jam that into the first element of this array. So I need to index this. It's off by 1. So again, just be a little bit careful. So again, when you go ahead and do this, yeah, this is exactly what we end up with, right? You see, you get 6 now complex numbers that we wrote up on the board, right? So you can do this here in Mathematica pretty easily. Mathematica also has the Fourier function to perform this calculation that will help us out a little bit. In fact, let me go ahead and pull up the help menu for that just to show you. So Fourier, it's pretty simple. All you do is just give it a list of numbers, right? We give it our 6 numbers and it should compute it for the Fourier transform for us. The only thing that's a little bit we got to be a little careful of is read the manual, and you'll notice here that the definition of how Mathematica decides to define the discrete Fourier transform is different than what we had on the board. So depending on what discipline you're in or what field of study, the Fourier transform might be defined a little bit differently, but it's just like we saw earlier. As long as you're consistent with the forward and inverse Fourier transform, you should be fine. What we should note here, though, is that you can actually change the behavior of this function Fourier by passing in another argument, which is this Fourier parameters, which allows you to change how it's defined. So again, here's the exact specifications on it, but really the thing we care about is we have a version of the Fourier discrete Fourier transform which is used a lot for signal processing. So this is what we're going to want to use. We're going to want to use these specific parameters to get the same Fourier transform that we computed by hand. So again, let's go ahead and do that. Right, that's my little note to myself here, is just to mention that. Really, what we're looking to do is this, right? I need to call Fourier, give it the list of numbers, but I got to also give it parameters here, which tell it to instead use the signal processing definition of the discrete Fourier transform. So again, if you do this, you get the exact same thing, and we're golden. Right? Okay, oops, sorry, let me cancel this. Let me go ahead and bring this up in MATLAB, because I know some people are more comfortable in MATLAB. Let me just show you a very similar situation. So let me go ahead and run my code. All I've got is a little bit of code, just setting it up, the exact same thing we talked about. I've gone ahead and got a little bit of plotting. This, in fact, is how I generated those graphics I flashed up earlier, so we can see the underlying signal, and then the red samples are the ones that we actually have. Again, I wrote myself a little function called function A. So this f should have all of my sampled numbers, right? So this is the sampled discrete signal in the time domain. Okay, and now I'm going to compute the discrete Fourier transform using what I'm going to call method A for now. We're going to get into some of these other methods in later lectures, but let's just look at the very simplest method to do this. And in fact, here it is, right? I just coded this up myself really quickly. Again, you just pass it a list of all of those n numbers. I'm going to go ahead and compute the number of samples, right? I can easily find that out from the length of this list. That's going to allow me to calculate the primitive nth root of unity here. And then I just need to drop into this double for loop that we talked about earlier. So as I go from k equals 0 to n minus 1, I'm going to start off and just start summing up the values of the samples with the appropriate power of the primitive nth root of unity and store that. So that's what we end up with. And in fact, I think this gives us the exact same thing. Let me continue. And I think, let me go ahead and say f hat method A. Yes, this is exactly the same thing that we computed by hand on the board or got in Mathematica. So all of these methods are consistent. While we're staring at this, maybe I will prime the pump and make a little bit of a teaser. I think anytime you see this double for loop, you might want to raise some eyebrows in terms of performance. And also, we showed on the board, right, you saw there were all these sort of, only the blue entries changed, right? Only this n and k are what's changing within this loop. A lot of these are constants. So actually, we're going to look in a future video of how we can optimize this and write this actually as a matrix operation rather than this double for loop. But again, that's probably a topic for another discussion. Okay, well, now that we've got this f hat, right, we've got this transformed version of the signal in the Fourier domain, what do these all mean? Let's go back to the board and talk about that. Okay, so now that we've got all those numbers, right, we've got the f hats, we know how to compute those, we saw how to do those. Let's ask, what do these numbers mean, right? How do we interpret these results, right? So you got to remember, going back, right, we said that the idea was we had these basis functions that looked like this, right? So those are the green continuous lines, right? They were basically, it's a cosine, it's a complex pair of sinusoids, right? There's a cosine and an I sine here, right? And it's got the angular frequency as we discussed earlier, right? Okay, so now the idea then is that what these coefficients are doing, these are effectively coefficients which are telling us how much amplitude and phase are associated with each one of these basis functions, right? So the amplitude, okay, of any given wave, right, it's just given by the magnitude of this complex number. But remember, you got to normalize it by the number of samples here in our formulation, right? And again, we're going to look at that in a second, where we're going to see this phenomenon where if you just take more samples, the size of these complex numbers start increasing, their absolute magnitude increases, but it shouldn't change the frequency content, right? So we normalize that here by the number of samples, okay? So again, all this is literally the amplitude of the cosine wave, and all you do is you take one of these numbers, right? If I want the amplitude of this first one, I just go ahead and take the real part squared, the imaginary part squared, square root it. That gives me the norm, or the length of that number, right? The absolute magnitude of that number, and then divide it by n, right? Okay, that cosine, this wave, also you could think about this. The other way is, this is cosine plus I sine. So you can use a trig identity to jam them together into a single cosine wave. That single cosine wave is going to have this amplitude, but it's also going to have a phase shift associated with it, right? So the phase shift is nothing more than the angle associated with this complex number, right? And again, you can compute the angle using the atan2 function or arctan. Again, you got to be careful which one you're using and what order of input parameters is it expecting. Again, remember, we had a full dedicated video on this idea of the 4-quadrant inverse tangent with angles. In this case, we're assuming that it is the y component followed by the x component. That's kind of the MATLAB notation. Okay, and then lastly, the thing that's important, right? We said that the angular frequency of this sinusoid, right, is just given by this, right? It's 2 pi k over the period, and the period was, again, just n times x, right? So these three pieces of information are basically telling us what are the basis functions that should hopefully make up this sampled set of orange dots. In other words, maybe I should write this down just to be explicit about this. In fact, let me do this here in another color. Maybe I will use red, since we got some of these red dots, right? So the idea here is that the overall approximation of the function, right, it should be each one of these things gives you an AK, basically cosine of omega k x plus this phase shift theta k, right? So this is one of the green lines effectively, and now all I got to do is basically sum this up from k equals 0 to n minus 1, right? So this is basically telling us the frequency content of each one of these sinusoids at the different frequencies, right? This is telling us effectively how much does this given sine wave or cosine wave contribute to the overall blue function or the orange dots, however you'd like to think of it, right? So again, what these numbers are encoding then, the Fourier transformed numbers, these complex numbers are giving us amplitude, phase shift, and a frequency kind of implicitly comes along with it, right? Really, these complex numbers are just giving us these two components, right? The magnitude and the phase are coming along with it. And yeah, that's what we've got. So maybe what we should do is let's jump back over to the computer and compute the amplitudes of each one of these 6 complex numbers, compute the phase of it, and then we can actually even build up this composite function, and we'll see if it has similar properties and frequency content of the original function, okay? So yeah, let's jump back over to the computer. All right, so we're back here in Mathematica, and again, I've just gone ahead and defined a couple of 3 functions, in fact, here, which are just going to give me the amplitude, the phase angle, and the angular frequency associated with one of these given basis functions. The only thing maybe I'll call to your attention here is the arctan call here. So in this case, this is opposite of what we had on the board, right? Because Mathematica's version of the 4-quadrant inverse tangent wants the x component first and then the y component. So again, this is one of these things you just got to be careful of depending on what computer system or software package you're using. Okay, so now that we've got these functions set up, we can basically go ahead and yeah, interpret the results. So let's go ahead and look at the k equals 0 case. So remember, this was the flat kind of the DC gain, the constant value. So again, if you plug in the f hat 0 into this, or the first f hat, right, the first Fourier transform number, I think that was it was like 33 or something like that, right? In fact, maybe for giggles, let's just go ahead and pull this up. Whoops, I want this as a pure number. Yeah, it was 33, right? So there's an amplitude of 33, but remember, again, this amplitude is going to be normalized by the number of samples, right? So it's this 33 here divided by 6, which gets you a number of 5.5. Okay, and it has a phase angle of 0, right? It's just a pure real number, and the angular frequency associated with it was also 0, right? So really what this is telling us, what that first Fourier transform number, right, the f hat 0, it's telling us about the constant DC gain number, right? So it's basically telling us the constant value that should be present is around 5.5. Okay, which is actually pretty close to what we had. If you remember the original function, let me pull this up, right? This was the original function that generated the data, right? And we said that, yeah, there is a constant value of around 5. So it didn't get it exactly right because I don't think we had enough samples and it was a little bit imprecise, but this is pretty darn close, right? So this is basically telling us that the first kind of basis function that was present in that signal that generates those samples is a constant number of 5.5, right? Okay, great. Let's just keep going. K equals 1 then. So all we got to do is repeat this process, right? But now look at the second Fourier transformed number, right? Which again, I can't remember exactly. Let's look at it right now. Wait a second. Hold on a second. Let me look at this. Yeah, it's this number here, right? It's the 5.6 minus 2.5i, right? So again, this thing has a amplitude, right, once you normalize by the number of samples, of around 1, has this kind of a phase shift, and it has this kind of angular frequency, right? So what this is telling us that there should be a component of it that's about like this, right? So this one is about, again, it's a cosine wave of 5.2 radians per second, and it has an amplitude of around 1, right? And this phase shift associated with it in radians, right? Okay, great. So keep going. K equals 2. You see, again, you repeat this process. Now K equals 2. There's a slightly bigger cosine wave, right? Because this amplitude comes out to be 1.5, right? And again, you can keep going, and yeah, you just keep doing this. Keep plugging it in. Keep computing amplitudes and coefficients. It's basically telling you how much of each cosine wave makes up the signal, All right, so let's do this, and now let's add all of these up together, right? I'm going to go ahead and create this g function, which is basically just adding up all of the different components of all of those different parts together, right? So let's do that, and then this is what you end up with, right? So you end up with 6 terms, right? So here is the constant value of 5.5. Here is the first cosine wave. This is the slowest cosine wave, right? It should be about this much. Then the next highest cosine wave, then the next highest, and then the next highest, and then the next highest, etc., right? So what's interesting is if you look at this, right, we can see that actually this cosine wave looks to be the biggest, right? This one here, oh, and I guess, let me see. Unfortunately, it looks like it didn't order these in an order of frequency, so this is a little bit difficult to interpret. I tell you what, let's go over to MATLAB in a second, and this will be a little bit easier to see. But what I want to do right here is I want to plot this and see how does this compare to the original signal, right? So that's what I've got right here. So here, blue is the original function, and green is this composite sampled function. And what's interesting is look how well it does, right? It actually is doing excellent at the sample points, right? And it looks reasonable, right? These two signals, the blue and the green, look like they have similar frequency content, right? Okay, this is actually bringing up a good point. We should ask ourselves now, which one of these functions contribute more than another, right? We remember from the original formulation that this cosine wave here only contributes a little bit because it's got an amplitude of 2, but this one contributes more, right? It's got an amplitude of 3. So we expect to see more of the 2 Hz signal than the 1 Hz signal. And in fact, you can even kind of see that if we look at this. Let me see. The 1 Hz signal, this is going to be something that's like, what is 1 Hertz? It's around 2 pi. So it's around 6 radians per second. So that's probably this guy right here, right? This one here is about, you can see right here, it's about 6 radians per second, right? And that contributes about, 1 unit, right? The amplitude here is 1. But then the 2 Hertz signal, what's the 2 Hertz? 2 Hertz is about double that, so it's around 12 radians per second. So maybe it's this, let me see, where is the 1.5? Here we go, right? This one is close to 12, right? And you can see this one's amplitude is bigger, 1.5, right? So this is seeming to line up. And again, this might be easier to look at in MATLAB. So tell you what, let's switch programs and let's do the exact same analysis just in a numerical tool. That might be a little bit easier to visualize. Okay, so we're back here in MATLAB again. This is the same script we just looked over, but now let's go down here and compute some of these parameters that we were interested in. In particular, I want to look at the absolute value of f hat. Okay, and I guess technically maybe what we should do is we should normalize this by the number of samples n, right? Let me make sure I have that defined over. Yep, n right there. Okay, great. So this is basically giving me the how much each one of these contributes. So tell you what, let me comment some of this out for now, actually, because we're going to talk about that in a second. I'm mostly curious about this component right here. So again, all I'm doing is I'm computing the frequencies, and then I'm just plotting. This is basically the amplitude of each one of these cosine waves, right? So if I run this, and we end up with something like this. And in fact, tell you what, let me make this a little bit easier to read. Let me make this bigger. Marker size 15, line width 2. Okay, this is gonna make it a little bit easier to see. Okay, so here we go. And now you see, okay, yeah, here is the frequency content, right? So we see that there's a big component, 5.5 of this 0 frequency cosine wave, that's the constant. And then here is the 1 Hertz signal approximately, and here's approximately the 2 Hertz signal, right? Okay, so that's interesting. And again, remember, notice this symmetry. There is some symmetry about this middle value, right? Just like we saw on the board, the reason is because one of these numbers is the complex conjugate of the other, effectively. So from an amplitude perspective, this is what we end up with, right? So this is extracting some of this. And now what we want to do is actually, let me show you that if we just increase the number of samples, so now instead of taking 6 samples, let's take 6D. Let's increase this by a factor of 10, right? So I can rerun this code again, and it's going to get us let me show you a couple of these plots. So again, here's the signal, right? So again, we're getting now, instead of 6 of these red x's, I'm going to get 6d of the red x's. That's what I'm going to go ahead and run through my discrete Fourier transform, right? So again, these are the 60 samples in time in the time domain, right? And then we're just going to go ahead and same thing. We're going to take the DFT just like we did earlier, and now I get 60 complex numbers, not just 6, right? And you can see these numbers are getting bigger. In fact, I can look at f hat of 1, right? The first one, this was telling me the constant value. Remember earlier, this was a value of 33. Now it's grown to 300. This is showing why we need to normalize this. And again, this makes perfectly good sense if you look at our equation for the Fourier transform, right? Let's come back and let me scroll up and let me find the equation, right? And if you go back to our results on the board of how we wrote this down, you'll see that what you're doing, right, is now instead of 6 things we're adding together here, it's actually 6d of them that we're adding together. So yeah, you're going to get a bigger number in general, right? And that's what's ending up happening. Okay, so that's why we have to normalize. But what's fascinating now is let's look at the plot of the coefficients, right? So here was the signals and the samples, but when we go ahead and plot the amplitudes of those coefficients, this is what we end up with. And bam, look at this, it nails it. Now this is telling me, hey, look at this. There's a frequency component here of 5, right? This is the DC gain number of 5. And now look at this. There is a frequency component here at exactly x of 6.2 radians per second. That is exactly 2 hertz, or excuse me, 1 hertz, right? So again, remember this here is this function here, right? Okay. So this x here is telling me that, hey, there is a signal of 2 hertz. Or excuse me, I keep saying 2 hertz. This is the 1 hertz value, right? And it has a magnitude of 1, right? This one over here is the 2 hertz, right? This is x of 12.5 or 12.6. This is 4 pi. This is right a frequency of 4 pi, right? So now this is saying, hey, this is 50% larger, which is in fact what is the case, right? Now what's interesting though is notice here that this amplitude is 1. Right? But we said here that the amplitude was 2, right? That's where you pick up the other amplitude here at the mirrored end here, right? So there's another higher frequency signal here which also has an amplitude of 1. And the reason we're getting this symmetry is a little bit due to this aliasing phenomena. So basically this one should add up with this one to get us an amplitude of 2 in the sampling, and this 1.5 should add up with this 1.5 to get us the 3 here. So this is fascinating, and this is really interesting that it's showing us the frequency content quite well of this signal. And again, the magic of this is, again, remember that we started out with the red dots over here, right, on the left, and that through the discrete Fourier transform, right, got us these red x's on the right, which is the frequency content associated with these red samples on the left. So again, really, really fascinating. I think this is really, really cool. Now, this plot here, this is going to start leading into some other discussions where we're starting to talk about things like the power spectrum and other analysis that we can look at. That's coming up in a future video. And also to bring up some teasers, we talked about, if you think about this, let's come back to our code, right? This might be giving you the willies a little bit because, right, think about this. You're doing a double for loop, and if the number of samples here, instead of 60, what if we had 600 or 6,000 or 6 million, right? If you had a lot, this could potentially be slow. So that's also going to bring up some issues. Okay. Maybe the last thing we should do before we leave is, I think we can do this here because this is pretty darn quick, is we should probably make sure that the inverse Fourier transform works as well. So remember, our inverse Fourier transform was just going backwards. So you should be able to go back if you have all of your f hats, all of your complex numbers. Again, you can use Mathematica inverse Fourier. Again, you got to make sure you give it the same parameters that you did for the forward transfer, and you should be able to recover the original values, right? And in fact, that's what I'm showing right here, is that you end up getting that. Of course, there may be some differences due to small machine error, and sometimes you get small, tiny imaginary components that you're going to have to chop off. But I'm just showing you here that in this case, yeah, the difference is very, very small. Right? So again, that is using a built-in function. Of course, you could code this up yourself if you wanted to. So again, over here in MATLAB, that's exactly what I did. I just went ahead and implemented a inverse discrete Fourier transform. And in fact, maybe let's put these two next to one another so you can see. What's a good way to do this? I know, let's put the inverse down on the bottom here like this, okay? So here is the forward discrete Fourier transform, and here's the inverse discrete Fourier transform. And as you can see, it's virtually the same thing. The only difference here is that in the forward transform, right, there was a exponent of negative, and in the inverse, it's a exponent positive. And then lastly, the only other thing is in the inverse discrete Fourier transform method, we got to normalize by n. Again, so that normalization comes back and we pick it back up here. So again, if you do that, you go ahead and you get the same thing. So I think this FA, oh actually sorry, let's go back to the case where we only have 6 numbers, because that's going to be more consistent, maybe easier to see on the screen. This is the original thing with 6 numbers. Sorry, let me comment this guy out. Okay, run this again, right? So we started out with F. Whoops, sorry, excuse me. I think I hit a breakpoint somewhere. What did I do? Hold on. Why is my MATLAB not responding? Oh, there. Oh, no, it is. Okay, sorry. Here's the original F, right? And then we ended up using the discrete Fourier transform to go F hat, right? And now we use this inverse discrete Fourier transform to go back to F, right? So F minus FA, these should be the same thing. And again, yeah, these things are small within some very small value, right? So perfect. So we went forward, we went backwards. Notice that there's a couple things that I didn't call out in this code that we will look at in some future discussions. Namely, again, it comes back to this idea of us coding this up by hand. Again, it's fun to do academically once or twice, but you really don't want to be doing this. You want to be using a package. In MATLAB, it's called FFT for fast Fourier transform, and the inverse is IFFT for inverse fast Fourier transform. And we're going to talk about that next, about what those things actually are and how they basically implement this discrete Fourier transform in a more efficient fashion. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. It really does help me continue making these videos if you do subscribe. And the new videos should come out every Monday, so I hope I'll be able to catch you at a future discussion and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.